welcome back. In the last class we had started looking at the specific equilibrium, which is the vapor liquid equilibrium. We are going to derive useful relationships at vapor liquid equilibrium conditions. We had already looked at a pure substance in vapor liquid equilibrium. We said that the conditions of equilibrium need to be valid, therefore Tv equals TL equals say T sat and Pv equals PL equals say P sat. This we are going to take as a given, and mu V equals mu L is what we said. We looked at this particular equation further, and using the expansions or the definitions of the chemical potential in terms of fugacity that we had developed in, or that we had given in module 3, we wrote mu naught plus RT ln Fv for mu V equals mu naught plus RT ln Fl for mu L, and we could see that the fugacities are equal of water in, or of the pure substance in the vapor phases and the liquid phases. From this and just the definition of the fugacity coefficient, we could write a relationship between the fugacity coefficient and pressure. Phi V Pv equals F sat, or in other words phi sat, phi V is nothing but the value at the saturated value under the conditions of vapor liquid equilibrium. Phi sat P sat equals F sat. This was equation 528, and what was left as an assignment for you was to develop similar expressions for a multi component system. This is for a pure component system, and you are asked to develop equations for a multi component systems. Hopefully you could do that, and let us see how they look at now. From mu V equals, or mu I V equals mu I L for a multi component system, that is the chemical potential of the species I in the vapor phase must equal the chemical potential of the species I in the liquid phase, and if we expand it as mu naught plus RT ln FIV hat, that is how we write the chemical potential is related to fugacity in the case of a multi component system. Therefore FIV hat equals FIL hat is what follows from mu I V equals mu I L. We will call this equation 529, and using equations 4.7 and 4.8 from module 4, you will realize what those expressions are. Mu I equals mu I hash plus RT ln phi I yi, this is what we got in 4.7 and 4.8, that is mu I naught plus RT ln phi I p yi 4.7, and mu I equals mu I hash plus RT ln gamma I xi. This is for the liquid phase and this is for the vapor phase, and for the liquid phase this further equals mu I naught plus RT ln gamma I fi xi. This is equation 4.8, or this was equation 4.8. We said that this is the condition, and if we, even if we do not look at it, if we just go ahead and equate these two, we get mu I naught will cancel out, RT will cancel out, therefore phi I p yi equals gamma I fi xi. This equation 530 is the condition for equilibrium of this is for a species I, you can write this for a species I at vapor liquid equilibrium conditions. So hopefully you would have gotten at this, if not, this is the kind of expression that we were looking for. Now let me give you some sort of a real world example and give you some time to work it out, and the answer is very simple, but it requires some bit of thinking, so I am going to give you enough time for that. The example 5.3 reads as: the volumetric oxygen transfer coefficient KLa of a bioreactor volumetric oxygen transfer coefficient, is denoted as KLa. KLa of a bioreactor is typically measured without cells being present in the broth. Air is bubbled through the broth and the oxygen gets transferred from the gas bubbles to the liquid broth. At the end of the estimation, the oxygen concentration no longer changes in the broth or the bioreactor headspace. Under such conditions, based on what has been learnt in the module, what can you say about the relevant thermodynamic property of oxygen? I have worded it this way for a specific reason. I would like you to go through what we have covered in this module and come up with a solution. The solution is very simple, it is a straightforward thing, it is a very simple thing, but it will require some bit of thought, especially when you are doing it for the first time, and I will just show you the solution when we come back. Okay. Hopefully you got that simple solution. If not, the thinking is something like this. Under the conditions given in the problem, equilibrium exists between the phases. Note that there was oxygen that was transferring from the gas bubbles to the liquid phase, and then after a while there is no consumption of oxygen anyway, and therefore the concentration of oxygen in the broth is not going to change, and therefore the consequently the headspace oxygen concentration is also going to remain the same. Therefore, there has been a condition of equilibrium reached between the liquid and the vapor phases, or oxygen in the broth and oxygen in the vapor phase has reached a certain state of equilibrium. So, these are the phases that are of interest here, the vapor in the head space and the liquid in the broth. We are interested in the thermodynamic property under such conditions, and of course, the temperature and pressures you need to appropriately look at, but we are not really going to focus on that. From one of the conditions of equilibrium, equation 526, we can write the relationship for the chemical potential of oxygen. This is what we are looking for, and this is what we are going to write. The relationship for the chemical potential of oxygen is going to be that the chemical potential of oxygen in the vapor phase must equal the chemical potential of oxygen in the liquid phase. This is the condition that will be valid under the situation given in the problem, and from this you can come up with something useful, but that is not in the scope of this particular problem. Okay. So, you would have had a chance to look at whatever we have developed in the context of a real situation. Let us move forward. See you in the next class.